An introduction to derivatives and using the power rule to find a derivative. Have an original function, looks like a cubic, and then our first derivative is the rate of change of the original function. So how is this function changing as x gets bigger? Well, the y's are getting bigger, and so the change is in a positive direction. So the first derivative should be a positive number until you get here. Then the function, the y values are getting smaller, so the first derivative will return negative values for you. Remember, the value of a function is its y value. That's always important. It's not the x value. The value of a function is the y that you get when you put the x in. When you go to the second derivative, it's the rate of change of the rate of change. So even though this function is increasing, it's increasing at a less and less amount, and then it really starts decreasing. So the second derivative is saying how the first derivative is changing. Yeah, we're getting positive, but it's getting less and less positive. So the second derivative is returning for you a negative value in here. Well, this will make a little bit more sense if we think of it this way. You have the original function. The first derivative will give you a formula for finding the slope of the tangent lines, and the second derivative will tell you about the concavity of the function. So that's how it describes the rate of change of the rate of change, and slope, which is the rate of change of y over x, is the first derivative. So the first derivative is the rate of change of the function. This is how the slopes of the tangent lines are changing. So let's see how that looks. What happens is this function, in this region here, the tangent lines are positive. If you have tangents to the curve, all the tangent lines are positive until you get to the minimum, the local min right here, and the slope of this is going to be 0. So right here, the first derivative of x, whatever this value is right here, is going to be 0. All these slopes are going to be positive. Well, once you get past this point, all the slopes are going to become negative. So that's how the first derivative works. Now the second derivative will give you concavity. So this graph is concave down. The slopes are getting smaller and smaller. There's a point of inflection here where then the function will curve upward. So the concavity is going to change that way. We can look at the power rule. To find the derivative of a function, even if it's just one term, you find the derivative, and we note it this way, by taking the exponent and multiplying it in front, multiplying the coefficient by the exponent, then reducing the exponent by 1. So there's the power rule as it stands right there. You can also write derivatives as dy dx, and we'll look at that in just a minute. So here, if we have this function f of x, I'm going to erase this little guy here. Erase this and this initially. We'll use that to explain something in a moment. So here's the deal. You apply the power rule to each term. So right here you take this 3 and multiply it by the 6. That'll become 18. And the exponent will be reduced by 1, so it'll become a 2. This exponent will get multiplied in front, so negative 2 times the 3. And this exponent of 2 will get reduced down to 1. So what's happening is there are 4 terms. This is a cubic term, quadratic term, linear term, and constant term. The cubic term will become a quadratic. The quadratic term will reduce by 1 in power, so it'll become a linear term. And the linear term of the original function will become a constant term in the first derivative. Any constant terms, the derivative of those go to 0, so they disappear. And the reason for it is this. If you think of this constant as being multiplied by the variable raised to the 0 power, because anything to the 0 power is 1, so that's still worth negative 28, we can apply the power rule by taking the exponent times the negative 28, 0 times the negative 28, and reducing this exponent by 1. Well, the moment we multiply by 0, all that goes to 0, so it goes away. So if you want justification for why a constant term, the first derivative is 0, that's it right there. So anyway, this cubic becomes this quadratic when you go to the first derivative. If you see the function written just as y being a function of x, then we represent the derivative as dy dx, and we say this is the change in y with respect to the change in x. And again, exponent multiplies by the coefficient, and the exponent reduced by 1. That linear term becomes a constant term, and the constant term goes bye-bye. Whoa, look at this guy right here. Let's suppose this is our original function. It is a cubic. So we see the black function written, drawn as a cubic function with roots at 0, 4, and 6. The first derivative, if we apply the power rule, gives us that right there. The second derivative is the first derivative of the first derivative. That's why we say it's the rate of change of the rate of change. First derivative becomes this right here. So one more quick deal. The first derivative explains the slopes of the tangent lines to the original function. Now all the tangent lines will have positive slopes until you get to that max right there. At that value for x, which is at 1.6 roughly, that tangent line will have a slope of 0. That's why this function, this first derivative function, it's a parabola, it's a second degree polynomial, and it hits 0. The value of the first derivative will be 0 right there when the tangent line to the original function is 0. So at any rate, we're going to look at this a little bit more in a minute. I'm going to take you to another problem, and then the last slide will come back to this if you want to see this, and we'll get a little bit more mathematical with it. But suffice it to say, if the original function is a cubic, then the first derivative is a quadratic, and the second derivative is a line. Now the second derivative gives you concavity. So this graph is concave down, so you're going to get negative values for the second derivative until you stop going concave down and change to concave up. And that's going to happen right here. You can see that the second function, the second derivative rather, the graph of it hits 0 right here. So when the second derivative is equal to 0, that is where the graph is changing from concave down, negative concavity, to concave up, positive concavity. That's called a point of inflection. So we're going to find points of inflection when the second derivative equals 0. We're going to find a local max when the first derivative is equal to 0, because that means the tangent line has a slope of 0. First derivative gives you slope. There's another place on this graph where the tangent line would have a slope of 0. That's down here. We have tangent lines with negative slopes until we get right there, and that when you just touch that point at the local min, the tangent line has no slope. So the first derivative is equal to 0 anytime you have a local minimum value, the bottom point of a dip on the function, or a local maximum. So as calculus students, that is going to be huge for us. We are going to be setting first derivatives equal to 0 to find where these tangent lines have slopes of 0, and that's going to tell us where the local maximum values for y are and the minimum values for y. So if it's a profit function, we want to say, where do we make the max profit? We'll set the first derivative equal to 0, and we'll find that. So before we go to the next slide, let's just at least look at this. If you bring this down here, not coincidentally, this graph, this parabola, which is the first derivative, hits the x-axis. It is equal to 0 at the same x value that the original function in black reaches its max point. And then again, this parabola comes back up and has an x-intercept to 0 right here, and that corresponds to where the original function has its minimum value. So very important, setting the first derivative equal to 0 and solving for x when the first derivative is 0 is finding the local max values, what x is to give you the maximum y, and the other x to give you the minimum y on this function. So those are very important ideas. Here's a simple application. Let's suppose a car is traveling down a highway at 80 miles per hour. So this is hours, and this is miles traveled. Now we tend to use s of t, so distance as a function of time. And let's suppose it's right here. The car is traveling 80 miles for every hour that goes by. So the total distance traveled after so many hours, you'll find that by taking 80 times the hours traveled, that'll give you the total miles. So if we've been traveling for 2 miles, we put a 2 in there. 80 times 2 implies that we are up here at 160 miles. We have traveled a distance of 160 miles. Now the first derivative, applying the power rule, changes this from 80t to just 80. The first derivative is the slope of this line. How is this line changing? Well, every hour that goes by, we increase by 80 miles. So the first derivative we refer to as our velocity. How is this function changing? It's changing at a rate of 80 miles. Y is going up by 80 for every hour that goes by because the x-axis is hours. So first derivative is a rate of change. We're driving at 80 miles per hour. Now the second derivative is the first derivative of the first derivative. And remember, when we take the derivative of a constant, we get 0. So why is it that the second derivative is 0? Well, here's why. We said that the second derivative is the rate of change of the rate of change. Do you agree that the speed, the velocity of the car is not changing? It's staying at a steady rate of speed or velocity of 80 miles per hour. It's not speeding up, so the graph is not concave up, and it's not slowing down, so it's not concave down. By traveling at a steady rate of speed, when the first derivative, the rate of speed is steady at 80 miles per hour, it's a constant, the derivative of a constant is 0. So it means that our change in the velocity is 0. We're not changing speeds, we're not changing velocity on the highway. But you compare it to this graph over here, this is a quadratic function bending upward, and so the distance traveled after t hours, we could do this. If we put 2 in here after 2 hours, and maybe this thing is remote controlled, it's solar powered, and it's got a rocket booster in the back or something, so this thing can go faster and faster. Starts out slow and it's speeding up. After 2 hours, 2 squared is 4, so this thing's traveling, has traveled a total of 40 miles after 2 hours. So the first derivative will say, how far did we travel? I'm sorry, I said that wrong. The original function will tell us how far we traveled, distance. Now, the derivative of that function, the first derivative is the velocity. So at the 2-hour mark, this is a formula for how fast we're traveling. We take 2 times 20, and at that moment in time, the tangent line has a slope of 40. 20 times 2 is a slope of 40, which means we're traveling 40 miles per hour. Now, this car is speeding up. So this time, the second derivative does have a value. We take the first derivative of the first derivative, that linear becomes a constant. This implies that our speed, our velocity will change. It'll become 20 miles per hour more for every hour that goes by. So it's 20 miles per hour, so 20 miles per hour squared. So this, because it's positive, is telling us that the car is speeding up. So that's how those first 3 things relate. First, the original function, in this case distance. First derivative is a rate of change, a formula for slope. This slope will change depending on where you are on the x-axis. The car is speeding up. And because the car is speeding up, this guy right here, does have a second derivative that is positive. So there's an initial introduction to why we use first and second derivatives, how they imply what they are, and how we apply the power rule.